Hello and welcome to another video. In this video we're going to be working on step-by-step directions from a binary tree node to another. This is kind of another weird binary tree question where you're trying to go from like one thing to another in some weird format that people aren't used to, so it's not just like a basic traversal. So you're given the root of a tree and you're given two nodes. And you want to write the path from the starting node to the ending node in the terms up or left or right. So like in this case it would be up, up, then right, then left. In this case, it would just be left. And so yeah, that's basically all you need to do. And how do you do this? So there's a few ways. The way I originally solved this problem is you can just make an additional data structure with left and right and parent node, and then you can do a BFS. So you just like fill in the parent node for every single node. I think that should be pretty straightforward. You just do a traversal and you put in a parent node for every single node. And then you do a BFS, and then you just end up here, and then in your BFS you just keep track of like the path. But it's not that great, and I think it's also n squared because you're gonna go BFS in a bunch of directions. Maybe it's not n squared. I guess it depends how you make your path, but let's say your tree was like this. Then you'd basically have to keep adding a character to the path, and if you store your path as a string, that would be n squared, because like if you have if you add characters to a string one at a time, you're recreating a string. So it's not the best, it's not super clean. So there's a couple better ways to do it. So let's get an example. So let's say we have like this guy, and we're just gonna have the two numbers we care about. So let's say we have like this number here. So we'll call this S, call this like E. So basically, the path from start to end is always gonna go through some node, right? So if they're on two sides, if they're on different sides of the tree, it's going to go through the root. If they are on the same sides, it's going to go through some other node. So you're always going to go like up. You could go down technically, I guess, too. But basically it's going to go through some node, or you're going to go down from the start to end, but all those are going to be the same thing, and I'll show you why. So basically you want to look for like the node that they share on the path. So in this case it would be like this. And I think this is called like lowest common ancestor of a tree or something like that. But basically there's always going to be one, and if they're on the same path, then the lowest common ancestor is going to be like the first node you encounter, if they're literally just you go from one to the other. So they're either going to be like from one to the other, or you're going to go up to some node and then down to your other node, no matter where you are in the tree. You know, if you're here, same thing, you're going to go through the root this way. So basically what you can do is, instead of making the whole another data structure, we can just get a path from the root to the first node and the root to the second node, and then we can use that information to do other things. So let's do a couple examples here. So let's say like it starts here, the ends here. So the path from the root to the start will just be left, left. And the path from the root to the end will be left, right, right. And whatever they share means that the same path is going to be used to get to both nodes. So because they both share this, like you can just go through the prefix, and as long as the characters are the same path is going to be taken, right? So to get to both of these nodes, you start off going left. So that means the lowest common ancestor is this node here. But we don't actually need the lowest common ancestor. What we need to know is like how to get to it. So if this is the path, you can just say like, okay, everything they share for a prefix, just get rid of that. So basically all we care now about is this left and right, right. So we're at some node, we don't really care which one, and from that node we go left to go to S, and we go right, right to go to the end node. And now from here, if you think about it, so if if this is not empty for the starting node, that means you're going to have to go up somewhere. So basically it means that because if you think about it, like let's look at some other case. Well, I guess we'll look at some other cases, but basically if this starting path is not empty, that means you're gonna have to go up to your shared node, and then you're gonna, because you went down from that shared node to S, right? You went left, like we're only recording a down path, and then from that, then you just follow this path. So the thing we want to return is basically the reverse of this. So regardless of if you have left, right, whatever, all these need to be turned into ups. So this will just get turned to an up, and then the right path is going to be the same, because once we're at that shared node, then the right path is going to be what it originally was. So it'll be like up, right, right. So just to recap, let's write down the steps. So step 1, get path for both nodes, or to both nodes from root. Get rid of common path to figure out the lowest common ancestor. Reverse all nodes, or you don't even need to really reverse, just take length of path left over to the starting node, and that is how much we go up, and then add this to remaining path to end node. So the basic idea is you figure out the path to the LCA node. You get rid of all that because you don't really care about that, because you know to get from the start to the end you're going to have to go through that node. Then we know the path from that node to the start because we'll have that left over, and we're just basically reversing it. So whatever that path is, it's always going to be down some way, and we're just going to be reversing. So if that path is like 3 or 4 long, we're going to go up that much. Then once you go to that node, then that from that node to here is just the rest of the path. So let's go through a couple more examples maybe. Let's go through some examples where they're like on the same path. Let's say our start node is here and our end node is here. So in this case, they're on the same path. So our start path would be right, and that's it, right? So start path is right, and our path to the end node is right, right, left. So like I said, we get rid of the similar area, and we're just gonna have an index to do that, so we're not actually gonna like delete it. So the start node has nothing now, and then the end node has right, left. That means you don't need to go up at all, and then you just go right, left. And that is the case, right? You just go right, left. So that's the case that they're on the same path and the start node is on the top. Let's go through the other version of that where the end node is on the top. So here the start node is right, right, left. The end node is right. Common is this region. So now this start node, you have to go, this is how you get from the shared node to the start. So the reverse of going right or left is just up. So it's going to be up, up, and then there's nothing left here. So it's just up, up, and it is up, up. And let's do one final example where they're in some different areas of the tree. So let's say it starts here and the end is here. Yeah. So in this case, to get to the start, it's left, left, left. And to get to the end is right, right, right. There is no shared area because you have to go up to the root here. And so for the start, the reverse is just going to be up, up, up. And then we're going to add from that shared node to the end. So hopefully that makes sense now. So the recap, just a level like what the code is going to look like, I'll show you. I guess it's a lot of code, so I'll just show you because I didn't want to code it in live because it's kind of long. So we're going to make a solution class, and then we're going to have a start path and an end path, which will just be a string. And then we're going to be building our path as we go. That's the other thing I didn't mention. So as we traverse, you don't really want to keep building strings, right? Because it's not efficient. But what we can do is we can build a path as we go. So for example, we can just have like a current path string, or a string builder, or a array if you use another language. And then like when you go left, you just add a left. You know, if you go right, let's say you add a right. And then anytime you return back up, you just pop off the last guy. And then if you want the path, then you do a join. So then you only have to join your path twice. Because otherwise, if you make a whole string, then you're going to have like left, and then you're going to have like left, right, and then left, right, left, or whatever. And every time you add a letter to a string, you're rebuilding a string, so that's unsquared. So the way to avoid n squared is just have an array for the path that you just push and pop off of to have your current path and then join into a string when you need it. So we're going to call this traverse function. So let's take a look at that first. So this is like the traverse tree. So we're going to have the node and then the start value we're looking for, the destination value we're looking for. So if the node is a start value, then we're going to take our current path and toString it. And I just made 2 class variables for start path and end path for that. So if that's the case, we're going to store the start path here. If it's a destination, and they can be the same value technically. I guess you can check for that earlier, but just still work with it. So if it's destination, then end path is just the current path to string. Then, I mean, you can make sure you don't go to null nodes. You can go down to null nodes, and if it's null, just return, I guess, other ones, whatever. So if the left isn't null, then we're going to add a left to our current path. Then we're going to traverse left. And then once we're done, we're going to pop the left. Then if it has a right, we're going to add a right, traverse, pop the right. So this will basically build these two paths for the start path and the end path. So it'll be from the root to the path. Then let's take a look at the rest of it. So we make an integer and we just say while our integer is in both paths and the paths are equal. So basically that gets rid of, if we have some common thing for both of these, like let's say we have right, right, left, this for one. The other one is like right, right, all rights. Basically what we're saying is the paths might not be the same length, but what we're saying is while these characters are the same and not out of bounds, let's keep traversing because we want to get to the index of the first character that's different, because that's going to be how you get from the shared node to the node itself. Okay. Yeah, so that's here. Then we just calculate how many steps we need to go up. So whatever thing we're at here, however many steps here, just the length of this string minus the index. So in this case, it would be 6 minus 2. So we have 4, basically just how many more do we have left for the start? Because the start is going to be reversed, right? If you go left and right and whatever to get to the start node, you're going to need to go to the reverse. You're going to go back up to that shared node. So we just calculate that here. And we just have a new result where we calculate how many nodes do we still have left in the start node to go back up. And then finally, the last part is however many nodes you still have in the second one. So the destination, whatever the shared region is, once you're at the next part, you're basically just going to want to take the rest of it because this is the path from that shared node to the destination, because everything in common was to get to the shared node. Once you get rid of that, then these are the paths you care about. So this all needs to get replaced by up, and this stays the same. And so that's what we do there. So definitely significantly harder, I'd say, than most tree problems because you're not doing like a basic tree traversal, you're doing a bunch of other stuff. So kind of a pain to get correct. Like I said, the other version is you can make a data structure with like a graph with parent nodes. So every node has a parent node as well, and then you can do a BFS or some other thing like that. Also works. But I think this is the best, and this is the fastest and the cleanest. And also something to learn in this video is that when two nodes, the shortest path between two nodes is basically you go from the first node to the intersection point, and then so you can just like draw out this path, figure out like what's the first point they intersect, and then the shortest path is going to be from the start to the point where they intersect, and then down to the end. It's always going to be like that. Yeah, so that's going to be, I think, it. And let's go through the time and space. So traverse is now linear time because we are basically pushing and popping onto the path. We only do the join once, here and here. So this is linear time. This is also linear time. And then building the result is also linear time. So this is just O of n, where n is the number of nodes. You can optimize your result or your traverse function where like if you found your 2 nodes, you can return early or something, but it's going to be the same big O complexity, so it doesn't really matter. And space is just a bunch of n's, right? So traverse is O of the height of the tree, which it could be completely one-sided. The path could be also completely one-sided. Basically, if it's all completely one-sided, it's going to be O of n. If it's not completely one-sided, then the space complexity is usually O of the height of the tree. So maybe you could say like this. I've seen people do this where like, it's like logarithmic on average. Because then what will happen is the start path and the end path will be logarithmic, and then to go from one to the other will also be logarithmic. So if this is like a complete tree, see this tree is like 16 nodes or something, or I think it's one less than double. Yeah, so 15 nodes, and the path here is 4, and the path here is 4. So it ends up being logarithmic, so it's like this path is log n, this path is log n, and the full path is just log n. Yeah, and then a path from a node to a leaf will be log n in a balanced tree. So I guess you can write it like this if you want to. Yeah, so let's see what this says. Linear. Curious if this one says n or h. Yeah, I guess you can't determine height of the tree, so n. Okay. Yeah, gonna be all for this one. Kind of an interesting one. And yeah, if you have any questions, as always, write in the comments. Oh yeah, I think what I'm gonna do is I'll just do the companies and there's a lot here, but yeah, I guess I'll just put them all in the picture in the future. That'll be easier than like popping up this tab all the time. So yeah, thanks for watching.